What degree do you answer with this question? Somewhat, or none, somewhat, a lot, right? We could treat that as nominal data, right? We really could treat that as nominal data. But if we sat down and we thought about it a little bit more, you know, none, some, a lot, that's an order, right? But the problem with that is we don't know the distance between none and some and a lot. It may or may not be equidistant, so I don't know if it's interval data, probably not. But if we were to think of that variable as what a psychologist would refer to as a latent variable, right? We can ask interesting questions of that same set of data to get a more rich story of what's going on. The other things that we can take into account are things like with respect to these adjacent category models and continuation ratio models. We can think about the nature of these variables. So continuation ratio models would be appropriate if you can think of some ordinal thing. So we have this concept of 1, 2, 3, but to get to 2, you have to first pass through 1. To get to 3, you first have to pass through 2. So we're going to take a look at that kind of model, looking at the birth weight data again. Whereas before we just split it into a dichotomous variable, low birth weight, non-low birth weight, and then what we're going to do is we're going to break those into different weight categories. So if I'm going to weigh 5,000 kilograms, what's a good sized baby?
3 kilos. Yeah.
3 kilos. All right, so 3 kilograms, right? To get to 3 kilograms in my developmental process, I first have to go through 1 kilo and then 2 kilo, right? So you don't start at 3 kilograms, right?
No, but ideally you're.
Huh?
I mean, when you're born, that's when you start counting, right? So if you're talking about birth weight,
okay,
you
fine.
don't weigh them when they're in Jenny's stomach. So.
Okay.
But sure.
All right. But you get the idea, right? So if we have this concept of growth, first you have to pass through these things to get to some order in the sequence, right? So we can build models to model those kinds of processes. Adjacent category models, they're kind of what they sound like. So if I have 1, 2, 2, 3, 3, 4, what's the probability of being in category 1 versus category 2, or category 3 versus category 4, which is different than a multinomial because we're taking into account the orderedness of the data with respect to these adjacent categories. So the conversation we were having before class started, you know, the more we learn, you know, the comment was, you know, I just thought you could just take some data, throw it through the computer and get an answer. And you know, what I'm encouraging you to do is be creative, be specific in your questions. And if you can ask a very specific question, there's probably a way to model your very specific question as opposed to do something that will address your question in a roundabout, very coarse way.
How are the first two different from each other?
Well, in the multinomial categories,
the cumulative, ordered, and
the adjacent categories, the ordered is what we refer to as a proportional odds model, whereas an adjacent categories model, we'll get to that. All right. So as I said, you know, you have the code. We're going to go through the examples in class here, but this I want to consider today to sort of be like a survey of these types of models, just to give you guys a sense of there are other things out there, right? And you may not know the name of something, but if you can conceptualize the nature of the thing that you're measuring, then push to find a model or a statistician or somebody who can help address your specific question. But the idea here is, you know, fit the appropriate model to your question. And you can, there are many, many interesting models. There are many more of these kinds of models. And incidentally, have you guys ever heard of a conditional logit model? A conditional logit model and the multinomial logit model are mathematically absolutely equivalent. Okay, all right, so let's first start talking about this multinomial. So let's just look at the name of it. Multi meaning many, and nominal meaning name. Now, gnome is the root of that, right? So these are just things where I have two or more outcomes, possible outcomes, or they're simply different in kind, mutually exclusive categories, black, white, purple, orange, green, without taking into account color intensity and where it fits on the light spectrum, right? Just if it's in color, you can think of things like political affiliation. Right? So we're going to use something like a political affiliation in this case to motivate our example here. Right? But the idea here is with more than two categories, there are a couple of strategies. There are a couple of strategies that we could do to analyze data that have more than two binary outcomes. Right? There's nothing at all, say, that would stop you from doing a series of pairwise logistic regressions. Right? A series of pairwise logistic regressions. So just like in the ANOVA, if I had 3 or more groups, I wanted to compare the means of the 3 or more groups, I could have done a series of t-tests, right? But the disadvantage of doing all those t-tests, one of them is that you're not using all of the data. When you don't use all of the data, you don't have what we refer to as efficient statistics. Efficient statistics. So an efficient statistic is something that will give you more or less the same answer, same point estimate, but the standard errors would be smaller. Okay. So when you use all of the data, you get more efficient statistics in the sense that your standard errors will be smaller. Standard errors convey the degree of precision of your estimate. Okay. So there's nothing wrong with doing these series of pairwise logistic regressions, but you're throwing a lot of information away. Right? So to motivate this example, let's assume that we want to look at one's political identification. So we'll just say Republican, Democrat, or Independent. Right? We talked about, well, I could compare using some predictors, Republicans versus Democrat, and in that analysis leave out the independents. I could do Republican versus Independent and leave out the Democrats and so on and so forth, right? Which is perfectly legitimate to do. Right? Perfectly legitimate to do, right? All right, so this is what we were talking about here. Another consequence of not having efficient statistics is that we lose power. And we all know what power is, right? What's statistical power? Exactly, it's the probability of rejecting a null hypothesis when it's false. So if you don't lose all of your data, there may be differences between groups, but you may not see it, right? So in some sense, you're shooting yourself in your foot. Okay. Right. So if you recall, and I know you've all committed this to memory, because that's how you guys are, these models should look very similar to you to what we saw last time, right? But the idea here is that we're looking at log odds. So this is the probability of being in category 1 or choosing category 1 versus category 3. The odds, the log odds of choosing category 2 versus category 3, and the log odds of choosing category 1 over category 2, right? But when we learned about our contrast matrices, we learned that if I have k groups, I only need k minus 1 parameters to fully identify everything that's going on, right? Well, in the case of the multinomial logic, that's also true, right? If I have 3 or 4 or 5 or 6 categories, I only need to estimate k minus 1 parameters for these kinds of things, right? So what we can do is we can estimate this third equation, the relative odds of choosing 1 versus 2, by looking at the difference between these two models here, these two parameters here. Right? So if you recall, when we did dummy coding regression, we might have come up with a model or an equation that looked like this. 7 plus 2x1 plus 3x2, right? So this is our regression equation. And let's say for the sake of argument, this is Republican. Right, that'll be our reference group. This is going to be a Dem, and this is going to represent an Independent, right? So when we use dummy coding, we interpreted the intercept to be what in linear regression? Is what? Well, how do we interpret that? It would be the expected value of when the person is Democrat, right? It's the reference group,
Yeah.
right? And then the 2 with dummy coding would be the mean difference between Republican and Democrat, and then the 3 here would be the mean difference between Republican and independents, right? Well, if I were a Democrat, I would, my Y hat would be 9, and if I were an independent, right, so I got the 7 plus 2, that gives me my 9. And if I were an independent, that would give me 7 plus 3, that gives me 10, right? So if I want to look at the difference between the Democrats and the independents, what I could really do is look at the difference between the 2 and the 3. Does that make sense? Because it's all based on it's the difference from some constant value. Well, that's how we can estimate the third equation without doing a whole bunch of extra models and running a ton of, doing a whole bunch of tough math. So I'll show you how to do that. Okay. So all of this is basically logistic regression. These are the probabilities. This is exactly what we went over last week, or for the past couple of classes, right? So, so these are taking odds, or here the beta 1, x1, these are log odds. I exponentiate them to get odds, and this is odds over 1 plus my odds gives me my probability, right? Okay, now if you were to look kind of quickly here, we would see that because the denominators are the same between each of the 3 probabilities, these probabilities will sum to 1. So in the binary case, we got a probability of being in this group versus that group, right? So if I had a 30% probability of dying of a heart attack, then the probability of not dying would be 1 minus that value, or 70% in that case, right? Well, we're just generalizing that idea now, and we're saying, well, I'm going to take a person or some entity, and I'm going to say, okay, there are several potential outcomes. And I'm going to take each person and split it, instead of splitting them into 2 probabilities, the probability of the event and the probability of not the event, I'm going to take that person, I'm going to split them now into K probabilities. The probability of having event 1, the probability of event 2, and the probability of event 3. If these are mutually exclusive categories, those probabilities then should sum to 1. Okay? So this is really nothing more than a generalization of the logistic regression. Okay? Okay. So this is the outcome of some code that I've given you. So let's look at that code a little bit. Let me switch back to here. And the data here are in a little bit different format than you're used to looking at. So let me explain what the data are. Okay, so here, in multinomial models, we analyze what statisticians refer to as profiles, right? So in this case here, I have 23 distinct profiles. So a profile is nothing more than the distinct, unique combinations of the predictors. Okay? So my first predictor will be whether or not the subject is male or female. So that's this column here. So if male is 0, 0 times male means not male, or female, 1 times male means that they're male. What do I actually model what's important here? Okay, I'm not interested in this business, or I'm not interested in business or punish or explain here, but punish here is a trichotomous variable. It's a trichotomous variable, and punish here is some indicator of to what degree to what extent do you agree with the death penalty? Right. So the categories of punishment are 1, 2, and 3. and there are going to be the outcomes are I favor the death penalty, I do not favor the death penalty, and I don't know, I'm undecided. Okay? I'm undecided. And then here we have the C1, C2, C3. All right? These are counts. These last three columns are the counts. So for C1, that's going to refer to Republicans, the number of Republicans who fit this profile. C2 will refer to the number of Democrats who fit this profile, and C3 will refer to the number of independents who fit this profile.
Maybe I'm just confused because things aren't lining up.
Yeah, it's not spaced up. So let me run this a little bit, and we can then look at we can browse the table.
Are C1, C2, and C3, do you get that data ahead of time, or is
Yes.
that something that you generate from
Well,
the
these are
first
counts.
three?
So look, what I'm really interested in is I'm interested in male, punish, and the outcome, and whether or not they're a Republican, a Democrat, or an independent.
Oh, I see.
So my
I see.
outcome here is females who are in favor of the death penalty. One Republican is a female in favor of the death penalty. There are 3 Democrats who are female who are in favor of the death penalty. There are 8 independent females who are in favor of the death penalty. Okay? So this is just a more compact way of storing data.
But each one of those profiles is not an individual person, right?
No, this represents the number of people.
No, like the
So
profile,
profile
because
1 and 2 are both female who are in favor. So.
Right, so what's going to happen, and that's because if I look at the original data, there's going to be more variables in here.
Oh, I see.
So essentially what's going to happen is that the computer, well, let me show you what I'm going to do.
so they're basically saying that there's 23 unique combinations of variables.
Of all of the variables.
Of all the variables.
Yes, yeah.
But it's more confusing because we don't see all the variables.
You do see all the variables, but you don't, I'm not keeping all of the variables.
Gotcha.
You're going to see what I'm going to do in a second,
Okay.
all right?
Wait,
Yep, go ahead.
when you set up these models, like the predictors always have to be
No,
categorical?
they can be mixed just like everything else.
Okay, so they could be like continuous?
Absolutely.
It's just a more compact way?
Yep.
Okay.
This is regression. Nothing changes. I can write down the model y equals beta 1 plus beta 0 plus beta 1, x1 plus beta. I can write down the model the same exact way, and my betas can be whatever they want to be. Okay? Okay. So what I'm going to do now is I'm going to reshape the data. Now the data look like this. Okay. Then what I'm going to do is I'm going to expand. Are you guys familiar with the expand command? So what the expand command is going to do, it's going to say, I see it says there's expand C. It's going to create 3 or 2 copies of this row. It's going to create 45 copies of this row. Does that make sense? No? Yes? No.
There are 44 copies.
Well, 44, so there will be 45 copies of this row. So since there's already one, it's got to make 44 more of them. So right now there are 69 observations in the data set. When I run the expand command, did I run that already? I didn't do that yet.
How does it know that C1, C2, and C3 can be combined, like when you say reshape long?
It's just a tool for,
Like when you created the C variable, did you have to do something?
yeah, because what's going to happen now is now I have outcome 1, 2, 3. Right, so my outcome is really political affiliation. So C1, when the value was C1, outcome will take the value of 1. When there was an observation for C2, outcome will take on the value of 2. It does that when by saying long C, that's shorthand for C1, C2, C3, create a new variable called outcome.
Yeah.
put in the value of the variable outcome the suffix of my C variable. Okay?
So you can only do that if things were named with the same.
Yeah. Yeah. Huh?
When you reshape, you have to have the same.
Yeah. When you reshape, the prefix has to be the same. The suffixes can be different. Right? So now we went from 69 variables, now we're down to 109, we increased them to 195 total observations. Make sense? Yeah.
The other stuff that you put in that line though, like I profile, male, J, up,
Oh, here?
yeah, what is that?
So basically what I'm doing is I'm pivoting on these three variables. All right, let me do it again. Here's the data, right? I'm going to hold these three things constant, and then I'm going to create three new rows for each one of these profile rows. Well, two new rows. One row will be the value of C of 1. We'll take the outcome will be 1. The second row will be outcome equal 2. The third row will be outcome equal 8. Does that make sense?
So they're just gonna say like 101Y, 101Y.
Yeah. Yeah.
Okay. So basically, in that first step, you're gonna go from 23 to 23 times 3.
Yeah.
What happens if you don't put in that I? Like you're just saying reshape, does it not just keep the other
It'll
variables?
just, yeah, it'll do. If it does, if you don't put these other things, it'll put them in it'll put them here. It'll keep them constant.
So does it come out any different if you don't put the I?
No. At least I've not found it to have any difference.
Okay. If you had more variables and you only put those variables in there, does it keep the other variables or does it?
Yeah, but it'll hold those constant. But the I just tells you what to pivot on.
And the J is the
No, it pivots on the I
right.
and then replicates based on the number of levels of J.
Here.
Okay. All right, so now we have 195 observations here. If I were to sum up all of the C variables, it ought to equal 195. That's the point here. Okay. Okay, then what I'm going to do is I'm going to make these things readable by a human. I don't need profile or C anymore. Get rid of that.
What kind of data comes in this format? Like what questions or what kind of data would you need to think, I need to apply this?
If somebody gave you data,
Okay.
right? Because originally the data looked like this, as we're looking at it now. But what, am I going to give you 195 rows of data?
I see.
Or if I give you the data this way, could you then take this piece of paper and give it to somebody else, and they'd have everything that they would need to do to replicate the analysis?
Okay.
And actually, in some statistical programs like SAS, for example, it'll actually run a different algorithm if you give it the raw data as opposed to the tabular data. And if you give it the tabular data, it can still give you the same results, but it'll run quicker. Because there are shortcuts and tricks you can do.
Wait, in the tabular form it runs faster?
Yeah. Because it doesn't have to, essentially, remember we did the ANOVA, and the ANOVA is nothing more than a shortcut to the regression when we did the sums of squares between? It's the same concept here. All right. So we have our raw data. We have male, punishing outcome, and we want to predict political affiliation from whether or not the person is a male and whether or not they favor the death penalty.
So label defined, but in that table, we didn't see the labels.
Because I didn't run it yet.
Oh, so you have to do define and then value?
Yeah. Okay. So then what I'm going to do here is I'm going to use the tab function, use the table function, and I don't know if you guys know, I think I showed you this before, I can create new variables So I'm going to say tab punish or table punish. And then what I'm going to do is I'm going to generate a new variable. I'm going to create that new variable. I'm going to call it P. So it's going to create a P variable for every level of punish. So when P1 equals 1, this ought to look familiar. This should look like dummy coding to you, right? When P is 1, this is for someone who favors the death penalty, otherwise not. When P2 is 1, that means they do not favor the death penalty, otherwise not. When P3 is 1, that means they're undecided. Okay? So the reason I'm showing you this is I want to, we can do,
Sorry, one step back. Why do you have the label male? Like, why is it twice?
label,
Like,
male,
label
male.
value,
It's
male.
the variable and the.
Yeah, so this is the variable name.
Gotcha.
This is the variable
gotcha.
definition.
Yeah.
Sometimes I get confused. So when I create my label definitions, so I don't get confused, I often create my label definitions and name them the same
The same
name
thing. Gotcha.
as the variable I want to assign to them because I'm not smart. All right, so we see what's going on here. All right. Now, so I want to run this code here. So now we know what these three things are. Okay. By the way, incidentally, another name for this multinomial logit model is called a baseline category model. Baseline category model. So essentially, what we're going to do here is the way that the model is fit is that it's going to compare the probability of being a Republican as compared to Democrat. It's going to compare the probability of being a Republican as compared to undecided. So the baseline category for which we're going to make our comparisons will be Republican in this case. That's why it's also called a baseline category model. All right? So to fit a logit model, a multinomial logit model, the command is mlogit for multinomial logit. And it's got the same syntax as before. So outcome is our dependent variable. Male it's binary, so I don't have to tell Stata that it's a categorical variable. And then punish is a categorical variable with more than 2 levels. So if I use the I syntax, it's going to expand the punish into a categorical variable. Otherwise, it would treat it as a continuous variable. So I run.
What are the P1 and P2, P3s again?
I'll show you. Okay. So this is what you have on your handouts if you can't see the board here. All right. So here I have. Remember, the baseline category is, well, in this case here, it's independent. Baseline category here is independent. So I interpret these as if they were 2 separate logistic regressions. Right? As 2 separate logistic regressions. So I interpret this male of, and these are logits, by the way, as 1.3. So males are more likely to be Republicans than they are independents. People who are what was 2 and 3?
2 was in favor and 3 was undecided.
Okay, so it looks like people who were undecided or in favor are more likely to be Republicans than that, and people who are undecided are more likely to be Republicans than that. All right. Because the constant is negative, this means that they're not male, they're not in categories 2 and 3. This would be the odds of being an independent. All right, make sense?
Can you go through the same thing with the bottom one?
Yeah, okay.
Sorry, what was that the concept again?
All right, so if you flip pages in your handout. This is what we're looking at here. Okay. So independent is my 0 variable, right? Males are more likely to be Republican. To figure out what are the odds ratios of a male being Republican versus independent, what would I need to do to this logit? I need to exponentiate that. So let me do that so that we get out of the log.
What's the question that you're answering with this?
Okay.
This logit? I know it involves sex, political affiliation,
We're trying to predict political affiliation
based on
sex
and
and
feeling about
attitudes
the death
and
penalty.
death penalty
Got it.
interest.
Got it. Okay.
All right. Okay, so here we see people who don't favor the death penalty, right? People who respond affirmatively to not favoring the death penalty are more likely to be independents, are more likely to be Republican as opposed to independent. The people who are undecided are more likely to be Republicans than independent, right? And then down here at the bottom, I'm comparing the binary outcome of independent versus Democrat. So here, if I compare independents versus Democrats, males are more likely to be Democrats than they are independent. This is a logit. It's a positive logit. So people who do not favor the death penalty are more likely to be Democrats. People who are undecided regarding the death penalty are more likely to be Democrats. The constants, the intercepts here are when they're not male and essentially favor the death penalty. So females who favor the death penalty are more likely to be independents as compared to Democrats.
The interpretation of that 1.215 next to Democrat male.
Here, yeah.
That's, males are more likely to be Democrat.
Holding political, holding
Yeah,
death
basically you've
penalty
already
constant.
controlled for death penalty views.
Yes,
right?
yes.
Because probably if you remove death penalty views, it would totally be different. I mean,
Could be. Then you'd have an omitted variable problem.
And so the only thing you can say about females in this model is if you hold it, if you're like saying the other things are 0, right? The
Not
only
0, just holding it constant. Making them equal at whatever level you want.
Since your p-values for Democrat punishment are greater than 0.05,
Here, yeah.
does that mean that your thoughts about the death penalty don't have an impact, don't really
Do not appear to be associated.
predict if you're a
Democrat.
Democrat?
Or an independent.
Wait, I'm still
Or an
confused about the female.
independent.
When you mean holding, because like what you just said is that if you're not a male,
Not a male.
and you
This,
don't
this
have-
would be 0.
0.
Male would be 0.
but you have to hold the other things constant to make
Well,
it
no,
equal.
here, I'm interpreting the intercept.
Okay.
To interpret this intercept,
Yeah.
it's when this is 0 and this is 0 and this is 0, which means I'm dealing with a female who is in favor of the death penalty.
But if you wanted to just be able to say the same things about females, would you have to run the model?
What do you mean?
Like,
Just say
'Cause-
female, because here we can say males are more likely to be Democrat than independent, but you're saying
but we can't say that females are more
likely-
likely to be, like, we can say like a male is more likely to be a Republican than an independent.
Ah.
But we can't say anything about a female's likelihood of being a Republican.
Yes, we can, because this is males relative to females. So if I were to exponentiate 1.23, all right, so I'm going to exponentiate this 1.22, 1.215. Males are 3.4 times more likely to be Democrats as compared to relative as males are 3.4 times more likely to be Democrat as compared to females.
Okay. Female is female.
They are more than, you could flip it around and say females are more likely to be independents as compared to males holding death penalty propensity constant.
It's the same thing with the death penalty thing,
Mhm.
about the value for one is
Yeah.
not there, but you're basically comparing those two
Yes,
to the value.
relative to the death penalty, yes.
And can you do the same, sorry, just to spell out what she was just saying, so if, like that
Okay,
1.6.
so I'll take this 2.7 because it's
Okay.
this
That's the
statistically
underside.
significant.
Okay.
So, so the odds ratios are 1.9, 14.9. So the bottom category is undecided here, okay? So when I compare someone who is undecided relative to someone who is in favor of the death penalty, undecided and holding sex constant, they are 14 times more likely to be a Republican as compared to someone who is in favor of the death penalty.
Favors one.
Yes, the omitted variable here.
Can you say that sentence one more time?
When I exponentiate this
Right.
2.7,
Yeah.
this gives me a value of 14, whatever. So people who are undecided regarding the death penalty are 14 times more likely to be Republican as compared to people who are in favor of the death penalty.
When holding sex constant, so that applies either
Yeah.
sex group.
I think
Yes.
what's confusing is how you can draw the comparisons between them being more likely to be Republican than independent, but really you're comparing it to females. So I'm confused as to
The outcome, so here I'm saying Republican, yes, no. If they're not Republican in this comparison, then they must be independent,
Okay.
right? Okay, to make this concrete, let's do a logistic regression, because I think you guys get that, okay?
Does anything in this table tell you about the combined effect of your sex and your feelings about the death penalty?
On your political affiliations?
Mhm.
Yes. Let's do the logistic
Okay.
regression, and I'll show you that, okay? So now I have outcome, okay.
Oh, that's probably the constant.
Yes.
This is the
No,
constant.
not necessarily.
Oh, okay.
Okay, one, this is gonna be, punish. If, okay, Democrat is what? What would I? Outcome does not. Oh, all right, good. I need to create a new outcome here. Outcome. I'm trying to do is I'm trying to do a logistic regression looking at, I know what I need to do, hold on a second here. Okay, so what I've done is I've now created 3 dummy variables for really our outcome. Okay? So political 1 is Republican. Here's what I need to do. Logit, outcome, male. Punish 1. So we want to compare Republicans versus independents, so I want to omit Democrats. 2 equals 1. Okay, that's what I've done here. All right, so what I did was I've created a new binary variable called political 1, political 2, and political 3. If political 1 equals 1, that means you're a Republican. If political 2 is 1, that means you're Democrat. If political 3 is 1, that means you're independent. Got it?
So right now, you're actually, for what you just wrote, you're comparing Democrats and Republicans, right? Based on what you just said.
Say that again.
Just keep going, never mind.
So what I'm going to do now is I'm going to do a logistic regression where the outcome is political 1. Oh, right, so I flipped it.
Okay.
So let me make that political 3. No, I want to keep it this
Okay.
way. I want to keep it this way. Okay, all right, so I'm now testing whether or not someone is Republican or not. To predict whether or not someone is Republican or not, I'm going to put in male, their sex, and their feelings about the death penalty. But I'm going to omit the Democrats. So this should say not equal 1. All right, so I'm going to omit the Democrats. So here we see males are more likely to be Republican as compared to females. People who don't favor the death penalty are more likely to be Republicans. People who are undecided are more likely to be Republicans. So let me write down these coefficients. So this is Republican versus independent. Right, and we have male in categories 2 and 3. And we have our beta, and we have our standard errors. So this is the multinomial logit. Do these numbers kind of look like those numbers? The reason that these numbers kind of look like those numbers is because it's essentially the same model.
Okay, which numbers are supposed
As
to
the numbers, this is from the logistic regression.
I don't know which numbers am I looking at.
So here are the betas from the logistic regression. This is the male logistic regression. This is the coefficient for not favored. Here's the coefficient for undecided. The reason that they're not exactly the same is because this model also takes into account the males that are Democrats, right? The other thing I want to bring to your attention are the standard errors associated with this model compared to that model. In general, the standard errors from this model are going to be smaller than the standard errors from that model. In general. Okay?
Can we go back up and look at the logistic regression real quick? So I can see. This is comparing Republicans to independents.
To independents. Yep.
And what was the code for that one? Just outcome, like, was it just the logistic?
Well, this was just a logistic regression. So let me do this to show you.
And did you use mlogit for this because there's more than two
Yes, more than
political
two
parties?
categories, yes.
Okay. So it's essentially the same thing as logit, it's just your, whatever you're predicting has more than two categories?
Yes.
Okay.
As a matter of fact, here, let me do this to hopefully drive that point home.
And the standard errors are smaller because you're taking into account more
All the
of
data.
Yeah.
So here's what I'm going to do. I'm going to run a multinomial model, but I'm going to omit the people who are Democrats. These are my coefficients from the multinomial model, omitting the Democrats. 139, 156, 285. The standard errors should be all the same. Why should they all be the same? Everything should be the same because it's the same model. It's the exact same model. Now, to drive that point home, I'll do a logistic regression. There's no difference because it's the exact same model. The reason that we do the multinomial is to take into account the fact that we have more than two outcomes, more than two categories of our outcome. And if I were to do series of logistic regressions, we see that our standard errors are larger. If our standard errors are larger, our z statistics will be smaller. If our z statistics are smaller, our p-values will be higher. We lose statistical power. Okay, does that make sense?
I totally get that they're the same thing. I still don't know if I have the answer to Dominique's question about how you would how you can tell what the effect of the question about how you could
how you combine all this
combine
stuff
all this information
into a female who is undecided, for example.
Sure.
Okay, pick a category, right? Let's write it down. Pick a group of people. Well, let's pick a sex.
Female.
You want to pick a female.
Yeah.
Who is, how do they feel about the death penalty?
They're not in favor.
They are not in favor. Female, not in favor. So let's write down our equation. We have an intercept of, can you read the intercept to me?
-3.28. Or do you want the whole thing?
Yeah, the whole thing. So what is it, negative, what is just the first negative 2.3.2.
3.28483.
3.28 plus, what is for male?
1.9.
1.39 times male plus,
Not in favor.
what was the coefficient for not favor?
5, 6.
1.56 times not favor plus, what's the coefficient for undecided? What is it?
2.85.
2.85 times undecided, right? This is our model, this is our equation. Now,
Okay.
okay?
All right.
You got the answer to your question now?
No, but,
No.
so it's predicting, what it's predicting is their political affiliation, right?
Yes,
Okay.
yes. So if I want to predict the political affiliation of a woman who is not in favor of the death penalty,
Mhm.
the equation will look like this. Negative 3.28 plus 1.39 times 0, because they're female,
Mhm.
that cancels out, plus 1.56 times
1. Because they're not in favor.
1, because they're not in favor of it, right? Plus 2.85 times 0, that cancels out.
Okay.
So the odds of a woman who is not in favor of the death penalty being Republican is, or the log odds are, negative 3.28 plus 1.56. So if I were to take that and exponentiate it, that gives me the odds of a woman who is not in favor of the death penalty being a Republican.
Versus.
Yeah, versus.
No.
No.
It's just the
Those are the odds.
Yeah, okay.
If I want to get the probability, I have to take those odds and turn them into a probability. 1 minus that probability will be the probability of them being in a independent as compared to a Republican.
So from the M logic, we could do the same thing under the Republican category as the
Yes,
Democrat
yeah.
category?
So if you want to get these probabilities, and if that's the simple question we're asking, let me do this. Let me run the multinomial, right? Then I can do predict y hat.
So from here, then we would just change those numbers instead. We would use the different constants.
Yep. All right, so if I do di exponentiate negative 3.28 plus 1.56, those are the odds of a woman who is not in favor of the death penalty being a Republican. Those odds are way less than 1. Not very likely that a woman who is not in favor of the death penalty is a Republican. Okay, so how do I turn that into odds or probability? The probability of that woman who is not in favor of the death penalty of being a Republican is 15%. 1 minus that is the problem of that same woman being a Republican, an independent. Right? Because that's what the logistic regression asks. Yes, ma'am.
So because all of these are doing like a pairwise
Yeah.
thing, is there a way of saying the woman, if there's a woman who is in favor,
Yeah.
saying Democrat versus Republican versus Democrat?
Yeah. So those are the 3 probabilities, right?
Yeah.
Yes. If you flip back to page they're not numbered, but it says multinomial logit. That's how we would do this. All right. Yeah.
So Oh.
Give me 1 second here, and help him lose it.
So you would just change your baseline group?
Yeah.
No, not necessarily. There's a way to get
That's
all the probabilities at once. Here we go. So to get all of those probabilities,
You're right, I don't understand how odds cannot have a comparator. Because isn't it an odds against something?
odds, well, it's this versus that.
Right.
Yeah,
How
so-
it's still not Republican versus independent.
It's a well, in this case, it would be the probability, well, whatever those odds are.
Yeah.
Whatever they computed them to be, are the
Yeah.
odds of being a independent versus Republican. That's not just a woman. That's a woman who is not in favor of the death penalty. That's what that 328 and 156
Right,
represent.
so this is the odds of a woman not in favor of the death penalty
Being a Republican.
So they're
versus-
0.1 something.
Versus being independent.
So they're like 0.1 something times less likely, the odds.
Hold on a second.
Because it was like 0.15.
Yeah.
Hold on.
Sorry, guys, for those who get that.
There's a way to get the probabilities for all three groups simultaneously without having to do that all yourself. I'm just trying to remember how to do it. I'll have to get back to you on that. It's a simple command. It's using the predict command. I just don't remember how to do it off the top of my head. Okay? All right. So the next thing we can compare is I can compare a Republican male. What's the difference between a Republican male and a Democrat male? Right, because now we were just looking from our multinomial logit, we were comparing Republican versus independent, Democrat versus independent, but we haven't looked at the effect of male in predicting Republican versus Democrat. Right, to do that, let me redo the multinomial again, and you see here I have Republican colon male, Democrat colon male. Okay, so let me explain what all that is. Here's my model. And remember 100 years ago when we were doing post-estimation commands for a Stata lab? There's a matrix that's left over. These are my betas. All right, so let me print out my matrix of beta coefficients. So this is the matrix of my beta coefficients. So what these should look familiar. These are the coefficients from the model that we did above. Okay. So this is the coefficient for a male Republican relative to independent. This is the coefficient for someone who's not in favor of the death penalty, of being a Republican as opposed to independent. This is the coefficient for the undecided, being a Republican as compared to someone who is in favor.
Is
right?
there any gender assigned to this comparison, or is
Yeah,
it
right here.
Well,
It's
like
here.
So when you say they're more like like the beta for Republican male being
Not a Republican male.
a male being
It's a male being a Republican holding death penalty constant.
compared to
A female. Okay, so here are my coefficients. What I can do is I can grab those coefficients and subtract them using this lin-com. Lin-com stands for linear combination, which should sound familiar because that's all regression is. So basically what I'm going to do is I'm going to create a new variable. I don't have to name it. I'm just going to say create this thing, and the null hypothesis is this difference 0? Right? Because a logit of 0 is 1. That means a 50-50 probability.
That underscore B just grabs the things from that.
The underscore B means it's the beta matrix, the matrix holding the betas. So now, when I compare a male of being a Republican versus a male being a Democrat, males are more likely to be Republican than they are Democrats. So this is the difference between those logits. I tested if that is 0. Is this 0? It's not 0. Well, it is 0. There's no difference between a male being a Democrat or a Republican. That's my confidence interval. Okay? And I can do the same things for Republicans, and I can do the same thing for the other variables in the model. So the next 2 lines of code that I gave you are, what's the difference between someone who's not in favor of the death penalty being a Republican versus someone who's not in favor of the death penalty being a Democrat? Well, someone who's not in favor of the death penalty, holding sex constant, is more likely to be Republican than they're a Democrat. That's still not statistically significant. This is when I compare the undecideds of being a Republican versus a Democrat. Here we see that undecided, people who are undecided with respect to the death penalty, holding sex constant, are far more likely to be Republican than they are Democrat.
Okay, maybe this is a really dumb question. The first thing, couldn't you do some of this with like a chi-square analysis, like looking at people, like if you're only looking at 2 categories?
You could, but you're not getting, you're just saying, are they independent?
Okay.
Which doesn't say, so if it's statistically significant that they are dependent, you haven't described the magnitude of the relationship between that dependence.
Okay, so when you've done, if you say like male Republican, male Democrat, you do those like in a chi-square with those, you only said that they are different, but not.
No. The question for the chi-square is, are they independent of each other?
Okay.
Right? But here, if you reject that null hypothesis of independence, that's all you can say.
Okay.
You can't describe the degree to which one is more likely to be one than the other. If you, and let me take your question to the next step.
Sure.
Some pieces of software, instead of computing a z-statistic, will compute a chi-square. It's called a walled chi-square. You'll see it walled. Since there's only 1 degree of freedom here, because I'm comparing groups, if I were to square this z-statistic, that's a chi-square. So in a sense, you are doing a chi-square test. So the chi-square test would give you this p-value, but it wouldn't tell you this.
Okay.
So yeah, you could do a chi-square, but you haven't extracted the same amount of information from the data. And to me, that's tragic.
Gotcha. So a chi-square would just tell you that if it was significant, that
And you get this, you should get more or less the same p-value.
that there was something about gender that influenced Republican versus Democrat.
Or some association.
Some association.
But you don't know the magnitude of that relationship. That's what the regression tells you. And if you were to square this, it's a chi-square statistic.
Okay.
Yeah. That's a great question. Right? Okay. Okay. Should we keep going until Andy kicks us out? You ready for the next thing? Okay. I don't see, oh, we don't have to, you tell me. All right, remember, this is just a survey of what's going on, all right? All right. So the next kind of model we want to use, now we're going to take into account, now we're going to say, we're going to make the assumption, or we have a belief, that the thing that we're measuring, the outcome, the categorical variable of interest that we're measuring, has some degree of order, right? So in the example I want to use here is I think I have a measure of happiness. So the scale that we use is a very crude scale of not very happy, happy, and very happy. And what I want to do is I want to look at the effect of marriage on someone's self-reported level of happiness. So not on a scale of 1 to 100, right? And even if somebody gave you get a Likert scale or a VAS, you guys probably use this a lot in medicine, visual analog scales. The visual analog scale looks like this. You know, none, all. Mark somewhere on this line where how happy you are, and you go, oh, I'm happy there. And then you measure the distance from none, which we believe to be 0. And we say, oh, this person's a 17 on happiness, right? Yeah, you raise your eyebrows too because you're calling bullshit on that, right? I am too, right? So the idea here is, the idea behind these visual analog scales, a VAS, is that since it's a measurement, it's a distance, it's really a ratio measurement. No, it's not. There's so much error in where people mark on that scale, it's not even funny, right? It's error. Right? If my hand slipped, oh, I meant to actually put the cross exactly here, but I put it there. You know, it's crap. So, are these measures that we're taking, are they really interval? Are they ratio? Are they categorical? Whatever, right? So you get the idea of what we're trying to do here. So the other thing here is with these cumulative logit models is that it makes this very strong assumption of proportional odds. A very strong assumption. So in the concept of proportional odds goes like this. Right? So say here, this line represents the spectrum of happiness. Right? The spectrum of happiness. Sounds like something SpongeBob would say. Right? So we have negative infinity happiness and positive infinity happiness. And if we were perfect beings, we could get the most precise measure of everybody on where they fit on this continuous measure of happiness, right? And let's say, for the sake of argument, we are gods, and we can scale this measure any way we want, and I'm going to say a happiness measure of 0 is average happiness, whatever. Well, but we don't have an infinite number of decimal places in our measurement. We only have 3 categories of happiness. What do we have here? We have not very happy, happy, and very happy, right? So what we're going to do here is that we can view this as a continuum. These become thresholds on this continuum of happiness. Right? Thresholds of continuums of the happiness. So what will happen, what we're going to try and do really, is that we're going to try and estimate where you are, excuse me, on this continuum of happiness based on where you responded on the scale. So the proportional odds assumption in this very simple model where I have one predictor, married or not, and 3 outcomes, 3 potential outcomes. So what will happen in this model is whenever you do a cumulative logit model, doesn't matter how many outcomes you have, how many categories of your outcomes you will have one set of beta coefficients and k-1 intercepts, cut points, constants, thresholds. we interpret the intercept. We interpret the intercept as where on this continuum are you? Where on the continuum, this infinite continuum, does the probability of responding in the lower category, not happy, happy, becomes a 50-50 proposition? All right, so if I were to draw the logit function, it might look something like that, right? This, you guys can't see around this, can you? So this is the probability, right? Probabilities go from 0 to 1. There's that S-shaped function here. This is the probability of 50%. All right? Where on the S-shaped curve does the 50% line meet with the level of happiness? That's how we're going to interpret our threshold. The proportional odds assumption here is that the slopes of those functions are equal. So it's a constraining function. Whereas in our multinomial model, we allowed the slopes and the intercepts to be different between each of the three categories, right? We allowed them to, because we had, basically we fit two logistic regressions in that last set here, right? So here we're saying, no. If you're married or not married, the probability in being in the lower category versus the higher category, the next higher category, is the same across the entire continuum. Okay, that's a strong assumption. That's a very strong assumption. And this is how it's very simple to fit these proportional odds or cumulative logit models. All right, so anyway, so you have the data in front of you, right? So we have this two-way table. I could do a chi-square.